In our last session, we had considered the frequency spectrum of non-periodic signals, and we had seen that in order to calculate this spectrum, you need to use the mathematical tool called a Fourier transform. Now in this session, what we are going to do is to study some examples and see how to calculate the Fourier transform of some given signals. That is what we are going to do. But before we do that, let us look at some of the salient points which we had touched upon in our previous session. So x omega, which is the Fourier transform of xt, is a complex quantity. So since it's a complex quantity, it has a magnitude and phase, and both these, magnitude as well as phase, these are functions of frequency. They are expressed either as functions of omega or functions of f, whichever happens to be convenient for the problem to solve. Now, plot of magnitude versus frequency is called the magnitude spectrum of the signal, and the plot of phase versus frequency is called as the phase spectrum of the signal. All right. Now, let's look at the notations. So, x omega can be written as magnitude x omega into e raised to j angle of x omega. And plot of mod of x omega versus omega, this is the magnitude spectrum. And this, note that this is an even function of frequency, because remember we had derived our Fourier transform starting with the Fourier series, and we had already shown that Fourier series, the magnitude spectrum is an even function of frequency. So the same remarks goes for the Fourier transform also. Its magnitude is an even function of frequency, which means mod of x omega is equal to mod of x of minus omega, even function of frequency. But the plot of mod of the angle of x versus omega versus frequency, this we call as the phase spectrum, and this is an odd function of frequency. This means that angle of x omega is equal to minus of angle of minus omega. So these are the notations. All right. So having looked at the summary of the Fourier transform that we had studied last time, let us now turn our attention to calculation of the Fourier transform of some of the signals. And the first one we study is a unit impulse. So suppose xt is a delta t, and delta t when plotted as a function of time, remember, looks like this. Before t equal to 0, it is 0. After t equal to 0, after this value again it's 0, and at t equal to 0 it jumps to infinity and comes back in 0 time. So this remarkable signal is called as a unit impulse. Now if you integrate this over all times, or in fact just before the impulse occurs and just after it has ended, if you integrate over this, the area under this is unity. That is why it is called as a unit impulse. This is something we have studied before. But what we want to do now is to obtain the Fourier transform of this unit impulse. So we substitute in our equation. Fourier transform of delta t is minus infinity to plus infinity delta t. Note that for xt, we substitute delta t e raised to minus j omega t dt. Now the impulse function has a property that if you multiply the unit impulse by some function of time and then integrate the product, then what you extract is the function of time evaluated at t equal to 0, which we call as f0. Now in this particular case, our function of time is e raised to minus j omega t. So if you substitute t equal to 0, there is e raised to 0, that is going to be equal to, that will be equal to minus 1. So if you calculate the Fourier transform of the unit impulse, the result that you get is e raised to 0, and that is equal to 1. Note that this is a constant. So this will be the value of the Fourier transform at any frequency. It's completely constant at the value 1, right from omega equal to minus infinity to omega equal to plus infinity. So notice this remarkable thing, that delta t has a pulse width in the time domain which is infinitesimally small, whereas its frequency spectrum has an infinite width. So this suggests to us that if we have a signal which is small in duration, then its frequency spectrum will be large in the width. On the other hand, if our waveform is large in duration, then its frequency spectrum will be over a smaller range of frequencies. Okay, so let us consider the inverse of this. Consider the impulse in frequency domain. So suppose we have the Fourier transform of some signal, the signal that we want to find out as a function of time, and let us say this is known to be delta omega. So an impulse in the frequency domain, and we want to find its inverse. So we write the expression for the inverse, xt equal to 1 upon 2 pi minus infinity to plus infinity x omega e raised to j omega t d omega. Now note that for x omega we substitute delta omega. So again we have the situation where this integral will be equal to a value which is e raised to 0, that is equal to 1. So this entire integral reduces to 1 and the 1 by 2 pi remains. Therefore, when you evaluate this, you get 1 by 2 pi. In other words, this tells you that if you find the Fourier transform of 1 by 2 pi, which is a constant, then you get an impulse in the frequency domain. So, if you have a signal which is constant in the time domain, what you really mean is that you got a DC signal. So this DC signal, its width is infinite, but it has got only one frequency component, that is at omega equal to 0, and that is impulse. So this is the other extreme of the case that we had studied. In our previous example, we had an impulse in the time domain which was having almost zero duration, infinitesimally small duration, and the range of the frequencies that in the frequency spectrum was infinite. And this is reverse. This signal is existing and has a constant value over all values of time, but has a frequency spectrum which is extremely narrow. In fact, you got an impulse in the frequency domain. All right. These two examples later on will have some application. But for now, this is our first example. Then let us take the next example. We want to calculate the Fourier transform of an exponential pulse. So this exponential pulse xt is defined like this, e raised to minus at multiplied by ut. So multiplication by ut implies that for values of time less than 0, xt is going to be 0. And for values of time greater than 0, xt will be equal to e raised to minus at, because then ut is equal to 1. And we want to find the Fourier transform of this exponential pulse. So the problem statement is find x omega, sketch amplitude and phase spectrum. All right. So we substitute xt is equal to e raised to minus at ut. So x omega is minus infinity to plus infinity xt e raised to minus j omega t dt. This is the definition of the Fourier transform. And we substitute for xt. So this is e raised to minus at ut. Now this ut can be removed by changing the lower limit to 0, because multiplying this signal by ut implies that the product has a value which is 0 for values of time less than 0. Therefore, if I change this lower limit to 0, I can remove ut from the expression. So x omega is equal to 0 to infinity e raised to minus at e raised to minus j omega t dt. So exponents add in this multiplication. So you can write it like this. Then you integrate. So this becomes minus 1 upon a plus j omega e raised to minus a plus j omega t, and then you put the limits. So when you put the limits, you get x omega is equal to 1 upon a plus j omega. Note that x omega is a complex function of frequency for this particular signal. So you can talk about its magnitude, which will be equal to 1 upon under root of omega squared plus a squared. Remember, for any complex quantity a plus jb, the magnitude is under root of a squared plus b squared. So in this you have a plus j omega. So the magnitude of the denominator will be under root of omega squared plus a squared. And the angle will be, for the denominator is tangent inverse omega by a, but since this is in the denominator, the net angle becomes minus tangent inverse omega by a. So you can see that as omega increases, you will expect the mod of x omega, which is the magnitude spectrum, to decrease. And here, as omega approaches minus infinity, this will approach pi by 2. And as omega approaches plus infinity, this will approach minus pi by 2. So let us look at the spectrum here. This is our exponential pulse, which is plotted xt equal to e raised to minus at ut. We have plotted only for the positive values of time. So this is how it will look like. And magnitude spectrum, we have already said that as the frequency increases, the magnitude decreases, and clearly this will happen for the positive frequencies as well as negative frequencies, because you got omega squared in the denominator. So now this particular graph that is plotted for a value of a equal to 2. Okay. Of course, if a is different, then this rate at which this decreases will be different. But right now we have plotted this for a equal to 2. And this is the magnitude spectrum. Mod of x omega equal to 1 upon under root of omega squared plus a squared. And as you can see, as omega increases, the x omega will decrease. So that is what is happening. And it will also decrease even if omega increases in the negative direction, because this is square. So even if omega is negative, this square will make it positive and the magnitude will decrease. And the phase spectrum, that is asymptotic to plus pi by 2 for negative omega equal to negative infinity, and asymptotic to minus pi by 2 for omega equal to plus infinity. So in this particular session, we have seen a couple of examples of the application of Fourier transform. So given xt, in one case we had assumed xt equal to a unit impulse, calculated its Fourier transform and plotted it. And in the second example, we have considered an exponential pulse and plotted its frequency spectrum. And that is all in this session.